sending biological material into space. The debate about whether life began on our planet has been going for a long time, whether it began that way. What is your personal view?
I don't think there's that much of a debate on whether life evolved on the planet. I think it's sort of the dogma that most biologists would believe from the evidence is that there was an earlier RNA world, and 99% of them believe that RNA world was here, and that the primordial soup on which chemicals polymerized into membranes and biochemistry and metabolism and finally into DNA all happened here.
Well, the question was about panspermia, right?
Right, but so the other side of it would be, oh, it didn't happen here, and life just sort of came to Earth.
Yeah.
And most biologists would say that's a very cowardly view. It's just putting the problem somewhere else, and it is cowardly, but it might be true. And the reason that so I happen to subscribe to that view, but it is a minority view. And the reason I subscribe to it is that if you look in the fossil record at where you first find sort of bacteria-ish things, where the general view is bacteria are quite primitive, which is, well, bacteria are way better than we are. They've transformed our planet. They've made an oxygen atmosphere. They do planetary science on a planetary scale, more than astronomers of planetary science do. But so that they happened, they were found within a few hundred million years of the core of the Earth. So that would suggest that you go all the way from raw chemistry to real biology in a very short period of time. So you have to say evolution, all the way bacteria is really dead easy, and it's going to happen over and over and over again. Or that, Earth is just a rich medium, and bacteria-ish things came from afar.
So a few hundred million years is too short of a period of time for you, and a few billion years is good enough. So because of this range, that's
right. Because it only buys you if life came from somewhere else, you get 10 billion years or so.
Right. But that's enough time for you to.
Well, I wish it was a factor of 100 and not 10.
Sorry.
Exactly. I'm against the Big Bang.
Natalie, Natalie, I don't know whether you're familiar with this paper of last week from Edinburgh University. It found that you maybe even don't need meteorites to spread life. The fast-moving particles are enough. What do you think about this?
So panspermia is this idea that life could have originated someplace else and then been spread to another planet. And it can do that either through collisions, lofting material into the air and letting it go on a course through interplanetary space, or as you've mentioned in this other paper, through more recent bombardment by dust in the upper atmosphere. It's seemingly counterintuitive, actually, when we consider this. It sounds kind of crazy, until you stop and realize that planetary formation is a very dynamic process. The early solar system, early epoch of planetary formation, you had planetesimals that were dynamically interacting both with each other and with their nascent disk. So it was a very violent and dynamic process. And that gas and dust clears out rather rapidly, but even today we have this remnant material. So you go through the calculations and you say, yes, it's possible, but I guess I would ask, is it necessary? I agree with Gary's viewpoint that it kind of violates an Occam's razor, if you will. I don't think it's necessary. Moreover, in the solar system, the process takes hundreds of thousands of years. So it's very slow. It's not very efficient. I find this technique much more intriguing on some of these other planetary systems that we found, like the TRAPPIST system, where you have 7 planets packed dynamically into an area that fits within, let's say, Mercury's orbit. So there, the transfer process is like decades, 100 years, not 100,000 years. So I think in systems like that, it's much more compelling.
And can you help me to visualize, so let's say, this asteroid coming in the atmosphere? Obviously, it's very hot, temperature is very high, and let's say there are some bacteria traveling there. So are they going to survive this last phase?
Well, that's the question, whether you're talking about a collision, which is very violent. So an organism, and we can think about either life, actual microbes, or maybe just organics. If we can take these complex molecules and allow them to survive these violent processes so that they can then seed life someplace else.
How they will survive?
Well, it's challenging. They're going to have to burrow themselves into the lithosphere of an object. They're going to have to survive.
Well, they should be a little bit underground, right?
Yes, right. And during their interplanetary voyage, they probably also have to be buried within the rock and then released rather gently as they collide back on the other planetary surface. So, the odds that happening are small. It's difficult, but calculations say that it's possible. I'm convinced that it's possible, and that these events happen frequently enough during the formation stages and even later stages of the solar system's life that it's possible, but hard.
So, Gary, do you agree that you kind of need to sit inside this rock and hide there for a while and then survive the lightning?
I mean, an asteroid smallish, a few meters across coming towards Earth is at 80 degrees Kelvin, and there's the Earth's atmosphere. Yes, it gets very hot, and the crust smalls off. The center is still 80 degrees Kelvin, right? Now, when it collides, there's a lot of energy released, but there's shock waves where there isn't heating, and Jay Malish has done lots of calculations, even experiments on this. So transfer of life by meteoritic exchange, it's hard, but it's not impossible. And the thing to keep in mind is that this revolution in exoplanets that you've been so involved with has been magnificent. It has all these hot Jupiters that are spewing planets like crazy. So movement between star systems can be entire planets. It doesn't have to be pieces of rock. If Earth got ejected tomorrow, we wouldn't do too well with the bacteria on Earth. We'd do just fine, thank you very much. And for a billion years to sort of hang out, they could do that.
Meaning that the Earth could be older than 5 billion years. So in that case, the Earth would be older than 5 billion years.
Oh, I'm not saying Earth was captured, but it's something analogous to Earth could see.
Something like that.
Yeah, it could go to the next planetary system. And, every star has an Oort belt around it, probably, and those Oort belts are very loosely coupled and exchanging like crazy as the stars sort of sweep next to each other.
Lyman, to sort of put some boundaries on how early in the life of the universe life would have emerged. We know that the universe is roughly 15 billion years old, 14 billion years old, rather, 13.8, 13.8. So at what period of time we can assume that now life can emerge? Probably not.
So something like that has to, the first stars have to form to make these elements of life. So something like 1 billion years, the process could start. And yes, we've heard about earlier. Early on is also a great time because you don't have to travel these great distances. Things are closer together, moving around a little more. So they could well start then and end up here, whatever, 13.8 minus 1 minus 4.5 billion years.
Okay. So basically now universe life had about 13 billion years to develop.
Yeah.
So Gary,
just one thing to add to keep in mind is the one thing that panspermia offers you is the ability to use what you know to look for life. Without panspermia, you'd say, oh, well, maybe there should be genetic storage. And genetic storage could be anything. But with panspermia, you say, let's look for DNA. And we have a $1 trillion industry that's really good at looking for DNA. So isn't it stupid to not look for DNA? Because we have such a great sensitive ability to do it. You know, we can find criminals with their DNA.
Now, again, assuming panspermia is the way to go, which you've been convincing the argument, the belief it's more likely that life here could have come from the other star system, like with this object which is now moving across the solar system that we all read about in the last few weeks, or you think it's more likely that it came from another planet orbiting the sun, like Mars? I mean, you're doing Mars sequencing.
The only place you can go over some of the outer planet moons. You're not going to go to, or you want to go to Alpha Centauri. I can't imagine going to Alpha Centauri to look for life, but you can go to the nearest planet to look for it. So exchange between Earth and Mars is sort of the most narrow view of panspermia. It's sort of bispermia. And so it's not nearly as, it doesn't bother you all that much, because it's pretty much anthropomorphic, anthropocentric, right? So, if you're privileging Mars, you're not much different than privileging Earth. So personally, I'd rather it came from somewhere across the Milky Way. I wouldn't posit it coming from Andromeda.
I feel like Gary needs some balance here.
Yes.
So what you're saying is that the exchange between galaxies is basically out of the question, right? So it has to be within one
I
galaxy.
can't imagine it, but early on.
But why is it necessary? I mean, the building blocks of life are everywhere, right? We look out into the interstellar medium, and there's already the seeds of complexity. We see them everywhere in the solar system. Carbon has very special properties. Water has very special properties. Why wouldn't the physical processes operate the same everywhere? Why do we need to invoke panspermia? I would ask. And going back to the question of the age of the universe and, how quickly does life take a toehold, I just wanted to point out one factoid that we now know, that there are planets that we have observed that are as old as the galaxy itself. That is, the galaxy formed in those very nascent moments of galaxy formation. Planets were already forming. The building blocks of planets were already there. And I would contend that the building blocks of life also were already there. And life should have taken a toehold almost immediately.
In a given galaxy.
In a given galaxy, that's right.
So that it existed 10 billion years earlier.
Right.
Well, on that subject, let's assume that galaxies are isolated. There's no change between galaxies, at least at this point in time. But within galaxies, it's very easy to get going relatively early on. So this would mean that in pretty much all the galaxies something should be going on. And in fact, there was this astronomer, Jason Wright, who did these sort of galaxies looking for signs of civilization. So his assumption was that those thousand spheres would be visible in infrared spectrum, and if there are enough of those spheres in the galaxy, then there will be some additional radiation coming in infrared. So he looked at those, at the number of galaxies, and didn't find any sizable anomalies. So Lyman, what do you think about that type of experiment?
As I say, just backing up, galaxies do interact, right? We see it all the time. We see trails from galaxies, smaller galaxies passing through us. I think there can be transfer there. But these, what are the limits? So I heard about this, and I think ultimately the limit, and I don't know much about Dyson spheres, but it seems like getting rid of the energy. I don't see any limit to making energy. It's how you get rid of it and survive. And so this is how it makes sense to me. That's how you look for it, right? Is to look at this in recognition, and that you don't see it or put some limit on it. That's the size of how big another civilization could be. So that makes sense. But that demands civilizations to have gigantic planetary scale energy harvesting.
Yeah.
Bacteria don't do that.
Well, I mean, the idea is to look at the craziest things we can imagine first, right? Because they're the easiest things. I mean, we have this Kardashev scale that was hypothesized that, we need energy. Complexity needs energy, and technology needs energy. So the idea that on a planet, maybe we will evolve to the point where humans can make use of all of the incident radiation from our star, the sun. And imagine taking that a step further and saying, well, maybe one day we'll be so complex and evolved, we will need energy, we will need to harness energy from the entire sun. And then Jason Wright took it further and said, well, maybe you can keep growing that complexity and evolution exponentially, and maybe you get to the point where you would want to harness the energy of an entire galaxy, or you would have life capable of harnessing the energy of an entire galaxy. And it sounds crazy, but it's worth looking, right? Let's go out and look at the galaxies. We certainly have surveys that have done that, and the White survey was one that did that. And look at the galaxies and see if you see anything weird. Are there any galaxies out there where there's anomalously low optical radiation emanating from stars, but a mysteriously high infrared radiation that's in the form of waste heat? So he did this study, and again, it might seem crazy, but it behooves us to go out and look. And then, as you might expect, he didn't find anything unusual. Okay, but so what, right? It doesn't mean that life isn't out there in abundance. It just means that these galaxies, or these civilizations that maybe have learned to harness energy from an entire galaxy are not common.
So any other interstellar or galactic civilizations we should be looking for?
Radical study. Heard about this happening, right? Something we should be looking. Looking for atmospheres on exoplanets is asking for sort of material like what happened here with the production of oxygen. That's very promising.
Yeah, there's different pathways for looking for life, and the one that I'm most tied to is the search for biosignatures. So looking for a global biosphere. That is a planet that has really become where life has transformed it into a living world so that you could see the global effect of life on the atmosphere. That's